Good morning, everyone. Welcome to the machine learning session. We have 3 great talks, and the first one is presented by Ziyu Wang on general pulse Taylor for simple power analysis based on reinforcement learning. The floor is yours. You don't have any control, okay?
It's myself, it's not this coach. Excuse me, we need a controller.
I have to.
Ah, thanks for the introduction. This paper is about general pulse Taylor for simple power analysis without reinforcement learning. It's a joint work by Yao Lingding and Wang Yue, Zhang Tongming Wei, Shao Weisun, and Li Haozhu. The process of SPA is depicted at the commit strip. Dr. Little AAC captured the pulse emitted by the device Little AAC and found that the pulse follow a regular pattern and caution Little AAC that such regularity can lead to easy analysis and compromise of the private key. As we can see, there are 2 categories of operations in these trees. The segment with single spike represent screening operation, and the segment with double spike represent the multiplication operations. As we all know, the power consumption during the execution of RSA is related to the private key. When conducting the SPA, the first step is to segment the trees and then analyze each tree segment. We use reinforcement learning to introduce a new method to automatically segment the trees. Let's provide some background on our work. Most all the existing literature only focus on automated classification of tree segmentation, of tree segment while neglecting tree segmentation. Thus, manual expertise still required to segment the trees, such as we need to manually identify the height of the peak and the minimum distance between each segment. This is quite tedious work. Our goal is to automate segment the trees and thus fully automated the entire SPA process. We use reinforcement learning, specific the DeepQ network, to achieve this goal. In Q-learning, the DeepQ network is used Q-learning to perform. And in Q-learning, take the video game, for instance, the little bird continue to move forward, and then reinforcement learning take charge of navigating the vertical movement of the bird to dart the obstacles. In Q-learning, we set the bird as the agent and the obstacles as the environment. Q-learning operates required 3 elements. First is the state. We define the state as the relative position of the current bird to the obstacles. Action refer to the movement performed by the bird upward or downward. We define the reward as the scores obtained immediately from the environment. In Q-learning, think of the little bird as having a little chat sheet in its brain. It's called Q table. The element in Q table is Q value. This value reflects the expected total return if the agent chooses the action in the state, such as in C2. Seeing those scores, the little bird swiftly chooses to flow upward. Initially, the table is inaccurate and filled with random numbers. As the bird keeps trying and learning from the mistake, it will use the reward to update this table with this formula. In the end, our little bird can achieve high scores. Although Q-learning is already powerful in many respects, but it still suffers from high time and space complexity. In order to deal with this issue, DeepMind innovatively used neural network to approximate the Q table, result in the deep Q network method. Standing on the shoulder of the giant, we developed a new automated segmentation method. Let me introduce the basic version of our work. Beside the target tree, the only parameter required as the input is the private key length. In our work, we set the tree tailor as the agent and the target tree as the environment. We define the states as looking forward from the current position to current red flag for a certain distance. Then the agent selects a distance within its field of version to jump to as the action. In order to improve the efficiency, we set the lower limit of the X range is f. F is calculated by this formula. This shows the state. Its analogy highlight the field of version around the character while you playing video games. In order to balance the exploration with the exploitation, we employ epsilon greedy math policy, with selecting an action with a maximum Q value with the possibility of epsilon, selecting a random action with the possibility of 1 minus epsilon. When the action is selected, the agent executes the action and receives the reward from the environment. The reward is judged by the difference between the current state and the already segmented trees. If the reward is negative, it will restart from the beginning. If the reward is positive, it will continue to move forward. The agent calculate the state, action, and the reward into this memory pool, and every 50 steps, it will use the experiments in the memory pool to update its weight, its neural network weight. Since there are many ways to segment a trees, in the end, after the agent mature, we can obtain multiple type of results. Let's evaluate our basic version of method. We conduct our experiment on 10 data sets, 9 of which are provided by us. The data allowed to release has been already uploaded to the GitHub, and you can access our data through this link. For the post-quantum data set, we use an open source data set, which I will discuss later. We are still refining our work, and more data set and codes can be found in our upcoming papers. First, we implement RSA on Sakuragi and collect the trees of Sakuragi during the execution of RSA. After running our method, we can get this segmentation result as shown by the red point. We found that there are 3 categories of segments corresponding to the operations. It's a little surprising that there are 2 types of modular square. This for modular square, this character for modular square for bit 0, and this character for modular squaring for bit 1. In order to highlight the difficulty of segmentation, we introduce random protection into the implementation of RSA, and we got this segmentation result. This demonstrates that our method has good universality. We then update our method into the enhanced version of our work. First, assigning all the tree segment into one seed can visual features. So we divide the tree segment into two seed, as shown by this figure. Maybe these segments are more closely than the others. So this segment will put into this seed. And it also allows us to recover the key. This idea follows that the public key algorithm often have two types of operations. In order to improve the efficiency, we recognize the seed using clustering algorithm periodically. Secondly, sometimes the segmentation process can't afford to accurately determine the end portion of the cartographic algorithm. So we use variance threshold with the Euclidean distance threshold to combine to find the end portion of the cartographic algorithm. Thirdly, sometimes the noise signal the noise signal may overlap in frequency with the segmentation features such as these sharp spikes. If the cutoff frequency of the filter is lower further, it will weaken the segmentation features as shown by the red curves. So to preserve the segmentation features while reducing the signal, we extract the envelope of the trees. Lastly, some segmentation results have some basis. So to improve the segmentation result, we set a point at the pole and allow the remaining segmentation point to align their vertical coordinate within a time range to align their coordinate as closely as possible with the pole. If the point can't adjust its voltage in a appropriate range, it will keep its original position. Let's take a look at the improvement made by the enhanced version. Okay. First, these trees of smart card during the execution of ECC. We use our enhanced version to segment these trees, and the sequence of the operand sequence recovered result and the segmentation result are shown in the first figure. The red point indicates the segmentation point. To visualize the operation sequence recovery result, we reduce them into two-dimensional use PCF method. And then we map the recovered result back to these two-dimensional representations. Cause our neural network can be reused, so our SPGPT can handle dynamic environment. After segment last trees, we receive the key in the smart card into 0xFF and 0xF0F0. And after we directly use our mature agent to segment these trees, and we got those correct segmentation result and correct operation recovered result. And because our constructor and the parameter of the neural network are relatively light, so we can directly load our neural network to the low performance platform such as laptop and Raspberry Pi. The time consumption of segment the last trees are shown in this table. It seems that our work can convert the trees into the operation sequence it seems that some sequence-to-sequence method can also accomplish this work, but to the best of knowledge, the sequence-to-sequence method required manually crafted labels for training. In order to make comparison experiment with our method, we collect 1,000 trees of the ECC for training. It can be seen that our method requires the least parameters and the least learning time and can achieve high accuracy. More importantly, we don't need any manually crafted labels. Then we collect the trees of smart card during the execution of RSA. To improve the efficiency, we use SOIT method to extract the leakage interval and perform reassessment based on this interval. This figure shows the segmentation and operation sequence recovery result. The blue and black segment represent the two types of operations in RSA, and the red segment indicate that the segment are incorrectly recovered but correctly segmentation. As we can see, the reward value corresponding to this error segment are relatively low. And we found that this due to the different geometric features from others normal and correct segmented trees by iterating over the operations in order of increasing real value, we can obtain the correct key within an acceptable time complexity. And those tree segments and in the two-dimensional visualization, we can see that those error segments corresponding to the outliers in this two-dimensional representation. We collect the trees of XY during the execution of RSA, and we extract the lower envelope of the trees, then perform our segmentation method to segment these trees. The red point indicates the segmentation result, and then we make the segmentation point back to the original trees. But as we can see that there are some discrepancy in the tree segmentation results. So we use fine-tuning method to optimize the segmentation result. As we can see, the noise part beside the leakage interval are reduced, so and it's beneficial for the subsequent analysis. We apply the fine-tuning method to all the segmentation result, and all of them achieve similar result as those trees segmentation results. After multiple rounds of selection, Kyber image as the only standardized KEM algorithm to date. For the algorithmic perspective, Kyber image high security, but when running on a specific device, it is still present risks of segmentation leakage. In our work, we only focus on the function of polyform message, which can be used to recover the message. As we can see, the mask and the coefficients of value varied based on the message bit. So we can use it to recover the message, then we can use the message to combine with some other method to recover the secret key. We use the trees from this paper, and we extract the lower envelope of the trees, then perform our segmentation method to segment this lower envelope as shown by the purple curve. The segmentation and the operation sequence recovered result as shown in the second figure. Combined with the chosen ciphertext in this paper, we can obtain the fully accurate and correct secret key. This figure shows the two-dimensional visualization. As you can see, there are two clusters, and this for bit 0 and this for bit 1. We summarize all the experiment results as this table, and we also conduct some comparison experiment with the traditional method, segmentation method. As we can see that our method has high security rate compared to the traditional method. To summarize, the only parameter required at the input of our method is a private key, and we can perform automated segmentation just use the private key. In our work, we proposed two versions of our work. The first is the basic SPGPT. It can accomplish many segmentation tasks, and if the segmentation result is quite inaccurate, we can use the enhanced version to optimize the result. The enhanced SPGPT include the enhanced environment and the value-based feature enhancement and the fine-tuning method. Any questions? Thanks.
Thank you for the nice talk. Any question from audience? I haven't seen anything from the chat. Please.
Thank you for the talk. I have a question about the reward. So is the optimal choice, the difference is the optimal choice. And in my experiment, some vertical bias could be occurred. So even the pattern is matched, but the vertical bias could be occurred. So did you consider another reward criterions such as correlation?
We compared the correlation matrix, Manhattan distance threshold, and Euclidean distance threshold in our paper, and the easiest one, Euclidean distance, often show good performance. So if you have any interest of this type of comparison, you can find the experiment in our paper. We show the different result in our paper. Yeah.
Thank you.
Any further question? Follow up on this? Let me check again the chat. So no question on that, but I have a few questions. Can you please go back to the second step that you had? The slide number I didn't write down. So please go back to the second step that you had when you were introducing the initial C that you have defined. You should go back really early in the set.
Of 6.
Back. You go and I will tell you. Okay, we are approaching. So one step backward, please.
This one.
Another one. Okay, here exactly. So on this slide, you define a certain distance between based on the length of the trace and length of the key. How have you decided for that? Is it the optimal choice that you have for the certain distance, or is it going to be refined by itself in the definition of a state?
You mean this formula?
No. Definition of a state, you have, yeah, exactly.
Yeah. Have you ever played video games? Yeah. When you control an character to fight the boss, such as sometimes the field of vision will highlight around you, the character you control. So based on this idea, we define the state this way. Yeah, it's very interesting.
Any follow-up on that? If there is nothing, I can ask another question at slide number 20.
Okay. Great.
We are approaching that. Okay. Oh, here you have the accuracy mentioned in the table. This is the accuracy of finding the right segment, or is it the accuracy of finding the right key?
Method. To find the operation sequence, corresponding to the private key. Yeah.
Okay, wonderful. So if there is no other question, we can thank you again for the nice talk. I think the next talk will be given it's not remotely, but we will see a recorded talk. It's unfortunate that the authors could not be with us today, but the talk is going to be given by Lichao Wu, and he's going to talk about weekly profiling side channel analysis. We cannot hear the video. Sound is muted or something.
This is a joint work with Guilherme Perin and Stefan Pisak. And now we first introduce the side-channel analysis. Side-channel analysis is a method that measures the physical leakage of the hardware and then trying to retrieve the secret information. Using this graph as an example, we have the input plaintext. The input plaintext is sent to the hardware that's running the cryptographic algorithm, and it outputs the ciphertext. The goal of an attacker is trying to measure the physical leakage of the hardware and then obtain using this leakage for the side-channel analysis. And finally, his goal is to retrieve the secret information, for example, the secret key. Profiling side-channel analysis is one of the most popular side-channel analysis method. Basically, there are two steps. The first step is the profiling step, which an attacker builds the relationship between the profiling traces and profiling labels. And then in the attack step, an attacker feed attack traces to the profiling models, and then the profiling model will output the probabilities of the intermediate data or the key, and then an attacker will rank the key based on prediction. The good things of profiling side-channel analysis is that it has the profiling phase and it characterizes the leakage, which makes the attacks really strong. However, the profiling side-channel analysis has its own limitations. The first and the biggest limitation is regarding the requirement of the clone device. In reality, getting a clone device that is fully controlled is really hard because normally the high security chips have this strict life cycle protections, and having a fully controlled device is nearly impossible. Connected with the first limitations, to construct the profiling labels, it requires the key knowledge. However, this key knowledge can only be obtained via the clone device. Without this clone device, the profiling side-channel analysis is nearly impossible to be performed in reality. Non-profiling side-channel analysis, on the other hand, do not have this limitation. The algorithm of the non-profiling side-channel analysis is really straightforward. So first, attacker will do the clustering algorithms on the attack traces based on the key guesses. Assuming that an attacker wants to retrieve a sub-byte, which have 256 possibilities, then he will guess the key 256 times, and then he will do the key ranking based on the specific matrix. The good things of non-profiling side-channel analysis is that there's no need for a profiling device, which significantly reduce the attack assumptions and make the attack more realistic. However, non-profiling side-channel analysis also have its own limitation. The major limitation is that it lacks of leakage characterization. Commonly, attacker will directly use the attack traces or perform the very limited preprocessing on the attack traces and then running the clustering algorithm. It is especially problematic when considering the higher order leakage or the leakage or implementation protected by the mask. Now we know the pros and cons of the profiling and non-profiling sidechain analysis, and we want to build an ideal SAA. How to do that? We think that an ideal side channel analysis should combine the advantages of both profiling and non-profiling side channel analysis. We want an ideal side channel analysis have limited text assumptions. For example, it shouldn't have any requirement on profiling devices. And in the meantime, it is able to characterize the leakage from the device under target. In this work, we introduce weekly profiling side channel analysis that combines advantages of both profiling and non-profiling SAA. Different from profiling or non-profiling side channel analysis, weekly profiling side channels analysis can perform the profiling without a clone device. We noticed that in some cryptographic algorithm, for example AES, the intermediate data is bijective to the corresponding plaintext. For example, in AES, the SBox output is bijective to the plaintext. We use this information to build the foundation of our attack. We first create a mapping function that can map the plaintext to the intermediate data by knowing the secret key. Thanks to this bijectivity, we can build our learning scheme. For the equation on the left, it represents the normal learning scheme that maps the input traces Ti to the output intermediate data. With this mapping function, we can actually replace the intermediate data in this equation to the mapping functions, which is map key star di. And here key star means the correct key. And then based on this new equation, because that this mapping function is controlled by k, and if we know the k, this mapping function is fixed, it do not have any influence on the feature extraction or the learning scheme. So we can simply remove these mapping functions, and now the equation become the to build the map between the input traces and the plaintext. And we call this model, or we call this the profiling model, plaintext-based model. And then we see the relationship between the plaintext-based model and the common model. We call it intermediate data-based model. The relationship between these two models is that there exists a mapping function key controlled by key that can transfer two models between each other. And ideally, these two models should learn the same physical leakage. Here is an illustration of the intermediate data-based model and plaintext-based model. For the intermediate data-based model on the left, an attacker just build or map the input traces to the sensitive data, which is key-related. However, for the plaintext-based model, the leakage traces is mapped with plaintext. As we mentioned in the previous slide, the connections between these two models is this mapping function that is controlled by the secret key. To really retrieve the secret key k, we need to know this mapping function. And it is a little bit difficult because you still need to guess a key. And now we have the problem how to do the key recovery based on the plaintext-based model. In this work, we introduce a novel plaintext distribution to solve the key recovery problem of the plaintext-based model. In the first step, we assume that the physical leakage traces follow the common assumptions in the side channel analysis, that the intermediate data is mapped by the real leakage model plus some environmental noise, Z. And now if the physical leakage follow the Gaussian distribution, which is another common assumption in the side channel analysis, then two intermediate data have relation based on their physical leakage values. Then we can use this Gaussian distribution algorithm to calculate the conditional probability of one in the intermediate data by knowing another intermediate data by measuring their physical leakage distance. Since an attacker do not know the real physical leakage, we replace the phi with the leakage model assumption denoted by M. And in this equation, which is the third equation, this the physical distance is replaced by the intermediate data distance. And now, since the target device have the fixed key k star, Then now we can calculate the conditional probability of the plain text instead of the intermediate data because the k is fixed. Since that in the third equation, most of the terms are fixed or predetermined by the physical leakages, we can simplify this equation and move to the fourth equation, which form the basis of the plain text distribution. Here, the plain text distribution is controlled by two factors, actually three factors. The first factor is a leakage model, assumed leakage model M, and the key assumption K, and finally the plain text. And if you see on the right of the equations, since that the secret key K is fixed based on the K assumptions, this plain text distribution is only controlled by the leakage model assumption M and also the plain text. Intuitively speaking, plain text distribution represent the ideal distribution if the leakage features follow the Gaussian distribution. And in that case, it can be used as the ideal distribution for the our prediction output of the plain text-based model. So in the last equation, we calculate the fitness between the plain text distribution and the predicted output vector of the plain text. And here, of course, we will make the different key guesses similar to the non-profile attack. And then the one with the highest fitness will be the correct key. And now we perform a case study to validate the method proposed in the previous slides regarding the key recovery. Here we simulate the attack traces and then make the different key assumptions. On the left part of the graph, we see that the predicted plain text rank correlated with the plain text distribution with the correct key guesses. Well, if the key guesses is incorrect, then the correlation do not exist anymore. Here is a comparison between the non-profiling, weakly profiling, and profiling cycle analysis method. As we mentioned before, the non-profiling cycle analysis do not have the profiling step, while the profiling side channel has this profiling step. Weakly profiling side channel analysis stands in the middle between these two methods by training or profiling and attack on the same device. Basically, the weakly profiling side channel analysis characterizes a leakage based on a plain text-based model and using this plain text-based model for the key recovery. So compare with the non-profiling side channel analysis and profiling side channel analysis, weakly profiling side channel analysis kind of combine the advantages of these two methods. Specifically, it do not require a clone device, and in the meantime, it can characterize the leakage. Here is the experimental result of the weakly profiling cycle analysis. We do the benchmark. We perform the benchmark with 5 public available data sets, and 4 of them are protected by the mask. Our benchmark is performed with both state-of-art non-profiling side channel analysis and profiling side channel analysis. For the non-profiling assays, we benchmark with the CPA, MIA, MOR, and DDLA. Note that for MOR and DDLA, they are both deep learning powered, but this method, it can be adapted to any profiling models like the Gaussian models or deep learning models. And for profiling side channel analysis, we consider both template attack and the state-of-art deep learning-based side channel analysis. When looking at the result, we see that for the non-profiling side channel analysis, our proposed method outperforms all of the considered attacks in both leakage models. And for the profiling side channel analysis, we see that our method is comparable to profiling deep learning-based side channel analysis. So we can simply draw the conclusion like for the non-profiling side channel analysis, the weakly profiling side channel analysis involves this leakage characterization step, which significantly boosts the attack performance. And when comparing with the profiling side channel analysis, it shows that the plain text-based model can learn a similar leakage compared with the intermediate data-based models. Then it lead to the similar attack performance. And also we test the robustness of the desynchronization of the weekly profiling cycle analysis. Actually, you can expect the performance because it follows the similar schemes as the profiling cycle analysis by characterizing the leakage. So it should have certain robustness to the desynchronization. And indeed, as shown in this table, we have tested two desynchronization level, 50 and 100. And in both cases, weekly profiling cycle analysis outperform the related works. In previous two slides, we show the superior performance of the proposed method. And in these slides, we study some critical parameters and show their influence to the proposed attack. First, we consider the data augmentation. Recall that for the weekly profiling cycle analysis, it cannot directly link with intermediate data because it relies on the bijectivity between the plaintext and intermediate data. So data augmentation is pretty important for the weekly profiling cycle analysis because the model need to use to learn the bijectivity and then move to precisely locate to the physical leakage of the intermediate data or K-related intermediate data. And the result shows that with certain data augmentation level, the performance of the weekly profiling cycle analysis boosts significantly, and it is robust in a certain data augmentation range. And regarding the data sets, similar to other profiling or non-profiling cycle analysis method, it's a data-hungry method, meaning that it requires a certain amount of leakage traces to do the key recovery. However, compared with the related work, we do not see a significant increases. Actually, they are comparable to the related works. And finally, we consider the training epochs because in this work we use the deep learning based method for the case study and to evaluate the performance of the proposed method. We see that for the training epochs, it do not really requires a lot of training epochs. Normally 100 to 150 is enough for the key recovery, and it can recover the key very efficiently. And now we move to the final part of this presentation, conclusions and future works. In this paper, we propose weekly profiling SDA, a middle ground between profiling and non-profiling SDAs. With profiling cycle analysis reduce the reliance on clone devices while retaining high performance by profiling on attack devices. In the result, we show that weekly profiling cycle analysis outperform the non-profiling cycle analysis and also reach a comparable performance compared with the profiling cycle analysis, which shows this really high capabilities in the key recovery. And also note that weekly profiling cycle analysis have reduced attack assumptions, meaning that it is more applicable to the real-world attacks. In the future works, we consider to improve the plaintext distribution models. And in the meantime, we want to adapt our proposed method to different ciphers and leakage models. Thank you for your attention, and this is the end of the presentation. If you have any questions, please feel free to send us email. The paper and code is available from the link shown in the slide. Thank you.
I would suggest that you contact Li Chao directly or other co-authors for any clarification that you may need or any question that you have. Now we can go to the next presentation that is also recorded. And the presentation is on an efficient shift invariant transformer network for side channel analysis.
Good morning, everybody. In this talk, I will present our work, Estimate and Efficient Shift Invariant Transformer Network, or SP. This is a joint work with Siddharth Choudhury and Dr. Devdi Mukwa. Over the last few decades, Side channel analysis has been widely researched in hardware security community. Over the years, many STA method has been introduced. And earlier, the template and stochastic attack has been introduced. Recently, deep learning based method has been widely explored for STA. It's turned out that the deep learning based STA has several advantages over the classical attacks. For example, in many practical applications, the trace length can be hundreds of thousands of features long. However, the classical attacks like template and stochastic attack cannot be directly applied on such a long traces. Therefore, some feature selection step is required before doing the actual attack to select a small number of informative features. However, in many practical scenarios, like in the presence of various countermeasures, such feature selection is not possible. However, deep learning based STA has the potential to eliminate the feature selection step by directly performing attack on long raw traces. Okay. Our work is following this line of work, which attempts to perform deep learning based STA on long raw traces. However, we also our model to be robust against various tutor-based countermeasures like random delay or clock jitters. Why do we need transformer network? To elaborate on the point, in a typical long traces, the informative features are spread across the traces, and to successfully perform the attack on such long traces, the deep learning model should be able to extract and combine the information from those informative features spread over the long distance of the traces. However, many deep learning models are not good at capturing such long distance dependence. Okay. For example, the convolutional neural network or recurrent neural network are not good at capturing long distance dependency due to their vanishing and exploding gradient profile. Feed forward network though can capture long distance dependency. However, they are not robust to jitter-based countermeasures. Therefore, we choose transformer network, which is known to be good at capturing long distance dependency. Here is a general overview of a typical transformer architecture. It consists of multiple transformer layers. Each layer consists of two major components, self-attention layer and position noise feed-forward layer. The self-attention layer takes a critical role in its ability to capture long-distance dependence. Okay, so to describe the self-attention layer, the input to a self-attention layer is a sequence of vectors, and the output is also a sequence of vectors. Each element of the output sequence is generated by taking the weighted sum of the input feature vectors, where the weights is generated using some softmax function of the pairwise similarity of the features of the input features. Therefore, the weights form probability vectors, and therefore the weights are also known as attention probabilities. How you can capture the long distance dependency? Suppose in the input sequence, D1 and D2 are two features which are informative, and rest of the features are noisy. Then during the training of the model, it can learn to give high weightage or high attention probability corresponding to the features which are informative, and it can learn to put low attention or close to zero values to the noisy features. Okay, therefore, during the summation operation, the informative features get summed and combined into some output feature. So in this way, any two informative features can be combined using a small and constant number of steps, even if they are arbitrarily long distance. What are the challenges of TN for SC on long basis? One major challenge or drawback of transformer network is its quadratic time and memory complexity with respect to precedence. It is a major drawback in SK domain, as in SK domain, the length of that traces can be hundreds of thousands of features long. So more precisely, in a self-attention layer, the n cross n probability matrix is computed, which requires for order of n square time and memory complexity. So thus, we want a better computational complexity for self-attention operation. So there is a line of work which attempted to make or improve the computational complexity of self-attention layer to linear is as follows. It divides the n cross n attention probability matrix into two matrix of size n cross d prime and d cross n prime. And then by reordering the computation of the matrix multiplication, one can easily verify that the computational complexity is reduced from n square d to n d prime d, where both d and d prime are much less than n. In terms of mathematical equation, it is equivalent to generalizing this softmax operation using some kernel between any two input features, where the kernel can be factorized into two vectors. And then after reordering the computation, one can achieve linear computational complexity. But we also want robustness against global random delay and clock jitter countermeasures. As we also want our models should be robust against these kind of countermeasures. So for that, our observation is that in the presence of those countermeasures, the positions of the point of interest or informative features changes, but their relative distances remain approximately the same. So to incorporate the observation into our model, our strategy is to incorporate relative positional encoding into self-attention layer, which will make it shift. So more precisely, so there is a line of work which attempts to incorporate linear positional encoding and while retaining its linear cost as follows. It generalizes the kernel to make it dependent not only on the pairs of features, but also dependent on their distances. And that kernel is chosen such that it is factorizable into two vectors. And then, then using the same deordering trick, one can achieve linear computational complexity while making the while incorporating the relative positional encoding. However, though there exists several such work, but there is a major problem of the history. To elaborate, we plot the histogram of the attention scores generated by one of such methods. From the histogram, we can see that the attention scores are mostly concentrated around 1. But what's the problem with it? In case of SPA, the informative features is sparse. That is only a few features which are informative and rest of the features are false. However, this kind of attention mechanism will do some kind of averaging over all features. So therefore, the informative features also get averaged with the noisy features, making the SNR of the output features low. Therefore, we want cell attention layer which has linear compressional complexity with phase length, incorporates the relative positional encoding and generate sparse attention scores. So that leads us to introduce a novel self-attention operation for SPA, which is named as Gaussian positional attention or Gaussian attention in software. So it is done in this way. So in this kernelized self-attention, we incorporate our own kernel function, which is denoted as KGPM, which takes the form of a Gaussian kernel and which is also approximately factorizable. Moreover, we approximated the denominator of this formula using a closed form representation and leading us to our final attention formulation like this. Okay, this attention has several property which is very much relevant to side channel analysis. First, its attention scores is sparse. Second, it allows long distance dependency. Not only that, by incorporating multiple such parallel Gaussian attention or multi-head Gaussian attention, one can easily increase the flow of information from features from one regions of spaces to distance regions, allowing its ability to capture long distance dependence. So now next we present our extranet architectures. So in extranet architecture, the input traces is passed through several convolutional layers, which is passed through several extranet layer and whose output is combined using softmix attention and which generates the final output. If you look into a particular extranet layers, it follows the general architecture of a transformer layers with a standard self-attention layer replaced by the multi-head Gaussian attention and the layer normalization layer replaced by the layer centering operation. The layer centering operation is also a novel introduction in this book. Next, we experimentally evaluate our extranet model. So for that, we have used 3 datasets. 2 corresponds to one first order mask implementation of AES, and 1 corresponds to second order implementation of the Clyde cipher. For the comparison, we have used 3 benchmark models, 2 of which are CNN-based model and 1 is LSTM-based model. First, we saw the results against the random delay countermeasures, and the experiment has been performed using an attack window of 10K. In this figure, we plot the guessing entropy with the increasing number of attack traces used for the attack. And as in all method as the number of attack increases, the guessing entropy reduces. However, we can see that exponent reduces the guessing entropy much faster than the other deep learning model, and the improvement is more prominent in the case 20 data. Next, we show our experimental results. The experimental results against random delay counter. However, in this case, we use a much larger attack window with size 40K. And as before, we have plotted the guessing entropy with increasing number of attack traces. And as we can see that on these two data set, ASCAR-F and ASCAR-R data set, the improvement obtained by Spanner is significant compared to the other deep learning DL models. Whereas on the CHES data set, though it's performing slightly worse than the LSTMnet model, but its performing is better than the other two models by a wide margin. Finally, we compare the models against clock jitter countermeasures. For that, an attack window of size 10K is used, and this table summarizes the attack results, which shows the minimum number of attack traces required to reach guessing entropy 1. In this case, all the benchmark model has been experimented using two setups. In one setup, the benchmark model has been trained and tested on the misaligned traces, and other setup, they have been trained and tested on a pre-processed traces, where the pre-processing has been performed using elastic align to align the misaligned traces. And in the result, we can see on the ASCAR-R, though extranet is performing slightly worse than FCNN with elastic alignment, but it performing significantly better than all other models. On the ASCAR-F dataset, it reduces the number of required attack traces to reach guessing entropy 1 by almost 90% compared to the second base performing method. And in the case 20 dataset, it shows an improvement more than 99%, showing the better robustness of extranet compared to the benchmark model against clock jitter count. In conclusion, SPA on long traces can eliminate the feature selection step. Transformer network is a good candidate for SPA. It can naturally capture long distance dependency, and it can be made significant. However, one drawback of transformer network is that quadratic complexity makes it difficult to scale for long traces. In this what we have proposed is extranet transform, which is a transformer-based model and which has linear computational complexity. Extranet is shift-and-change, making it robust to random delay and clock jitter countermeasures. Has been evaluated against several combination of masking, random delay, and clock jitter countermeasures with less than up to 40K. And the results demonstrated improvement of more than 90%. In future, we want to adopt Transnet for further longer traces with features more than hundreds of thousands features, and adapting extranet for SPA against shuffling and random delay interrupt countermeasure can be also an interesting direction of path. Thank you.
So for this paper, again, please contact the authors if you have any question. Unfortunately, we can not have a deep dive into the papers. I hope you have enjoyed the recordings, and the first talk was also very nice. Now we can just conclude this session with a round of applause for all the speakers of this session. Thank you.